how to make non-sequential models in TensorFlow using Keras. Let's get into it. So first thing we got to do is specify we're using TensorFlow 2.0, TensorFlow version 2.x. Make sure that works. Import TensorFlow as tf. Import TensorFlow.keras as k. And let's do the same with the layers as L. What else do we need? Let's use load tensorboard. Does that work? Yeah, that worked. Great. Okay, so now let's get some data. Training data and some test data, and we're just going to get that from data sets MNIST. Yep, load data, super easy. Okay, so we got that. We need to clean that up. Oh yeah, I need NumPy to clean it up. Import NumPy as MP. So let's clean up that data. Xtrain equals Xtrain divided by 255. And then we want to reshape that to be 28 by 28 by 1. And we want to do the same for test. Great. So that should work. And then our Y train is going to be and this will change it from being one hot encoded to one hot encoded instead of sparse. 10Y test, and that should be good. Okay, so that's all of our setup. Let's just label it as such. Setup, great. And then here, let's make this the model. Yeah, model code. And then let's just make that smaller. Okay, so that was all the setup. Now we're actually getting into the model. We have some data, so let's just make a basic model first. Let's say our X input is going to be a layer, and it's going to be an input, and we know it's 28 by 28 by 1. Great. I don't know why I had to commit that. Oh, first thing I like to do here is backend dot clear session, and also I'm going to rm-r logs, because we're going to use the tensorboard, so I just want to clear that out when we make our model. Okay, so we're going to make our model. We have our input. Let's just make a really simple model first and then add to it. So this is going to be flat branch. So we're going to make a flat branch first, make that work. So our flat hidden layer, flatten is going to be, we're going to use the flatten function, and we're going to take X input. So what that's going to do is it's going to flatten the input. So it's just one dimensional. Flat hidden. Let's make a hidden layer, L.dense. Units, let's 128 units, why not? I don't know. Activation, and well, let's just do sigmoid, because we're going to pretend it's like the 1980s. Oh, and then we need to, so this part here, this just creates those variables, and we need to tie that whole unit to the previous one. And so we say flat flatten, and that's how we tie it to the previous one. Just like here, so this just defines this layer with its variables. Flatten has no variables, and then this tells you what the input should be. Okay. Flat out is going to be another dense layer, and we want this to output as many units as y has, which is 10. That's what we had from up here. And activation, well, activation is going to be soft max. And again, we need to tie it to the previous layer, flat, hidden. Okay, so now that we have all of that, we can make our model. This is just one branch. We're going to eventually make a conv branch, but first let's just make this sure this all works. So this is going to be a keras model, and the inputs are going to be x in, and the outputs are going to be flat out, and that's it. That's our model. Great. So now let's take our model and we need to compile it, which means we need a loss function, and for a loss function we're going to use categorical cross entropy, yep, and we also need an optimizer, and let's just use Atom. I mean, we could use like RMS prop, or we could use stochastic gradient descent, we could use a whole bunch of other stuff, but that's how we're going to compile it. Oh, and let's add some metrics, or rather one metric, which is accuracy. And we've got it compiled. Last thing we need to do is fit the model to the data. So our data that we're going to fit it to is x train and y equals y train, and then our validation, V-A-L-I-D-A-T-I-O-N, validation data is equal to x test and y test. Okay, well, that's not really our validation data, but whatever, we're going to use that. Let's run it for two of those 2 times, and then there's something else I want here, and what is it? I can't remember. It is callback, right? Because we want to get this go to tensorboard, callback_tensorboard. Great. And we're just going to use default for that. So that should all work. Let's just make sure it does. It should compile and do something. Why isn't it doing anything? Okay. Hello? Okay. Nope. Logs. Okay. Yeah, no problem. Is it still doing something? Let's just runtime. Change runtime type. GPU. Okay. Yeah, it's doing something. Okay, here we go. Let's change that. Okay, so 93% accuracy, 94% accuracy. Okay, there we go. Done. And let's say tensorboard logs dir is logs. I think it's log dir. Yeah, log dir. It's logs. Whew. Got slow. What the heck? Okay. Something's going on. I don't ever remember it being this slow. Okay, here we go. Great. And we can take a look at our graph, and there we've got 2. Why do we have 2? I don't know. This is supposed to clean it all up. Oh, because this didn't actually run. Okay, great. So we have just one path. Ignore the second one, or look at the second one, ignore the first. Anyways, so there we go. We've got that. So that's just one. Now let's make a second path. We're going to do, this flattened dense off of the input. And in parallel, we're going to do a convolution branch. And so let's do a convolution branch. So we're going to call that conv and L dot conv2d. I don't know how many filters, 32, and kernel size, let's do 7, and activation is sigmoid, because we're still going to pretend that we're in the past. And so this again, this defines the function we're going to do and the variables, but we need to now tell it where it's going to get its input from, like that. And then let's do something similar. Let's say max pool 2D and just the basics. And we need to tell it where its input is coming from. Okay, so just so this is going to take, it's 28 by 28 matrix, and it's going to turn that into 22 by 22 matrix. And this is going to take 22 by 22 and turn that into an 11 by 11. Okay, so let's do that again. And this is going to be conv, and let's make this, I don't know, like 64. Let's make it a little bit smaller of a kernel size. So this will be 11, and it's going to change it into 6. And then this is going to take that 6 and turn it into 3. Did I do my math right? No. I did not. So this is 11, and then 11 minus, this is going to be 7. Yeah, I don't really like that. Oh, what? Let's make that 6. So this will be 6. Great. And then that turns it into 3, and then this 3 will go to 1 because we'll do 3 like that. And make this go 128. How did I come up with this architecture? I just made it up. It's not a great one. Okay, then conv out is going to be conv dot, L dot flatten conv, and no, this is not the output, this is flat, and then conv dot out is going to equal the same. We're gonna do the same thing that we did up there here, and it's dense 10 units, softmax, and this is gonna be conv flat. Okay, so we have our input, and then our input is fed into this branch, and our input is also fed into this branch. And then we're not going to use f out. We're going to use something combined, comb out. Okay, so let's combine them. So how are we going to combine them? Comb dot max. No, concat is let's just concatenate the two together. Let's say let's just do a max. Let's do comb out equals tf dot L dot maximum of flat out and conv out, and it just does the maximum of the two. Okay, looks good. And then conv dot out equals L dot activation, and we are going to use soft max. And then here, let's just get rid of this activation, and let's get rid of this activation. Okay, let's see if that works. Did I type it all in correctly? Oh yeah, so we've got to create it and then pass the value. Same here. We have to create it and then pass the value. Can I remove logs? Yeah, blah, 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 blah. Oh, I've got to create it and then pass the value. Calm out. Oh my goodness. Okay, here we go. Yay, it's doing something. And yeah, so we'll run this tensorboard after, and what we should see is we should see that from our input we get these two different branches, and then it combines it, and then it combines it and puts the output. Okay, so we got something. Now let's update this. Updating. Wow, it's so slow this time. Okay, let's just jump to graphs. And here we go. We have, look at that, we have the input, and it goes along two different paths. It's a non-sequential. We have, it does this convolution, max pool convolution, all of that, and then it does this flattened dense, and then another dense. It does the maximum of the two, and does the activation and our output. So we have two totally different paths that it takes. That's pretty cool. And we're going to make it a little bit cooler. What we're going to do is, instead of taking the maximum of these two, I am going to, I'm going to do something a little bit different. Bear with me for a second. What I'm going to do is I'm going to pass that through a dense layer. Let's say dense units 10, activation equals soft max, and this is conv out. Let's get rid of this. So it's going to go through these dense layers, and we're not going to do a maximum, we're going to do concatenate. So we're going to concatenate the two from here and from here, and then we're going to do one more dense layer here. And let's make this a little bit more, let's make this a little bit more, and let's add some something to that. So we've just, so this output now is not an actual, it's not saying what the output is. It's not estimating y. It's just this, internal representation, and here same thing. And then we concatenate those two, and then we come up with our final estimation. And that'll work. Let's just run that. Show you that it all compiles. It's all fine. Yep. Okay, so this is what I wanted to get to. Let's say this dense network here and this dense network here, we want it to use exactly the same values, but we want it to go through this branch, and then to do this. We want these two values to be exactly the same. No problem. Remember, I said that this is just defining what the weights are. So we can do that. We could say, we could create this thing. We could say internal final shared weights is equal to this guy here. And just to make sure everything's good, input size is equal to 128, because we were expecting the input to be 128. So now we can take that and we can paste him in here, and we paste him in here, and these two will share their weights. Let's take a look at that. Input size, input shape, it's not size. Shape. Let's do it. Okay, so it's running. Then after it finishes running, we'll take a look at what that looks like. It'll be a little bit different. Notice that there's two different dense layers here. It's not going to have those two different dense layers. Let's just zoom in a little bit. So this dense layer, we have 128 features coming in, and then this dense layer turns it into 10 features. Same with this one, 128, and it turns it into 10. We're finished training. Let's rerun that. Let's take a look at this tensorboard. Let's go to the graph. I don't really care about that. And here we go. This is what I want to show you. So we have the input here, comes along, and this comes along. And this dense network here is actually shares those internal weights that this tensor, that this unit has. So let's take a look at that. Can I do that? Yeah. So what's happening is it's doing this matrix multiplication, but it's got the internal value. It's internal matrix, the weights for this matrix multiplication, the m and the mx plus b, and this is the b, right? And that the values of that are being sent over into this matrix multiplication. And so this matrix multiplication here, it doesn't get its own weights. It reuses the weights from this guy. And so these two are completely bound together and they share weights. So when the gradient descent comes and gets feedback from the loss and it comes through this, then these get updated accordingly. Wait a minute, that doesn't look right. Supposed to do concat and then go. Let's just take a look at that. Combine out. Oh, this is comb out. Comb out. Okay, we want to combine that and that. Okay. Made a little mistake. We'll rerun it. We'll see that the graph comes correctly here, and the concatenation should then go to the loss. Okay. Ran. I think I could have just hit like the refresh. No, I can't because I deleted the log file. I've had that problem before. Okay, yeah, so here it is. So this is the dense layer from the first time we used it. Then the second time we use it, we're still using the same weights. So you see the weights are being transferred there. Can you see that? Probably not. There you can see that. So the weights are these two tensors that are being sent from here to here. So they're sharing the same weights, the same m and b. And then they are concatenated, and then our final dense here, and then our output. All right, that's it. That's our code. That's how you can do non-sequential and TensorFlow using Keras. All right, hope you liked it. Ciao.